intensive.
effect of
Some
milling
of them,
time for the copper
the
tungsten carbide
process
nanocomposite.
unfriendly,
As we
and
can see from the
it will
SEM
also
image,
affect subsequently in the
at
production
A,
for
the particles
environmental
is
issues
large,
will be affected.
where
But
white particle is
these problems
tungsten.
which should
Okay,
be
actually
taken care of. So therefore,
copper
you'll
and
find
tungsten
that
is immiscible system.
the
So
biological
when we
method
increase the
within the
milling
enzyme
time up
technology
to
approach
60
should
hours,
also be
okay, the
considering
white particles become finer.
some of
The
the
same
factors for
similar
economic
observation when
development,
increase
but at
the
the same
milling
time,
speed,
sustainable
we can
process has
see
got
that
to be considered, and that is one of the reasons
fine white
we talk
particles become
about
decreased,
solid state
where we can
fermentation,
see
because
at
solid
D.
state fermentation depends strongly on
Okay,
agriculture
and then the
waste
effect of
as a
ball
substrate.
size on the copper
Now,
tungsten
let's have a look at
carbide
some of the methods
nanocomposite. We
in the
can see
enzyme
that
production. As I was saying,
crystallite
the
size
major,
and dislocation density change,
two ways of
where
enzyme production,
internal
although
strain
it looks simple, but
we
nevertheless has not been very
increase, and then the
successfully
crystallite size
transformed or
decrease.
translated for
However,
commercialization, production of high
the ball
volume
size
bulk
and
enzyme
the ball
production.
size did not
Now, if you look at
change very much
this one,
on the
it is
effect
using
of the powder.
using
Okay, let's see for
substrate
effect of
which are
BPR
from the
on
environment
the
waste
nickel
material,
alumina
which are from
nanocomposite
the
system.
agricultural waste,
From
for
the
example,
SEM image,
through solid state
we can see that
fermentation. This is a
the
very easy
reduction of
process,
the particle
nevertheless,
size when
but
we're using
to transform this
20,
for bulk
1
production,
and
for
40 to
commercial
40 to 1
production, it
ratio.
is
Okay.
it's quite
And then
complicated.
effect of PCA,
You can have
titanium
a lot of processes
aluminium
using tray system,
alumina
for example, as shown
nanocomposite.
in the picture at the side.
When we see,
Not
when
only for
we can
enzyme
see that
production,
A,
but there are
B,
also
C,
products
G,
that you can
and
produce
E
from
is
microorganisms
powder
like
milling
organic
with
acids,
PCA,
fine
and
chemical,
F with no PCA.
biopesticide
We can
from
see
post
that
mushroom
the particles
production,
is
animal
large,
foods, fertilizers,
and
and a
then
lot of
effect
other
of the
microbial
atmosphere,
products that can be
on the molybdenum selenate
produced from solid
nanoplates.
state
Okay, we
fermentation.
can see that
Now, solid state fermentation
not
is
much
simple,
different in terms of the
cost-effective,
SRT
it's
patterns,
friendly
but with
environmentally, high product
microstructure,
concentration because limited volume
milling at 20 hours, showing that
within the
ammonia
system, and it is
gives
also easy to
large
purify,
particles than
no less
argon atmosphere.
contamination risk, but
Okay.
and it's
So
also wide
there is
application, wide use for a
two
lot of
terms
products.
that sometimes people confusing
Now,
about
schematically, you
high
have
energy
this
ball milling.
route where you
Actually,
can
these
start
two terms
with the fungal
use
potential
the
fungal
HEBM,
or organisms
but
that you want to
different
work on.
goal.
Define your
For mechanical
substrate,
alloying,
develop
we
the
want to produce
inoculum,
alloy
and
formation or
for
nano-structured
bulk
or
purposes, there should be
nanomaterials.
an SF
But
fermenter.
mechanical
This
chemistry,
is
we just
the
want to
bottleneck.
achieve the
What kind of
chemical
fermenters are
reaction.
we talking about?
And then materials used, we use the metal ceramic powders,
downstream processes,
and then mechanochemistry,
and
we use
before we go for
organic or
commercialization. Now,
organic
the thing
compounds.
is,
The process
the
type,
SS fermenter.
mechanical alloying involve of
Now,
physical
this
mixing,
is
and
I'd just like to
mechanochemistry
share
involve
some
the
of the
chemical
findings
transformation.
that we have
Field
worked
of
on, for example,
use,
mainly on
metallurgy
lipolytic enzyme,
for
for
mechanical
example.
alloying and material
We
science,
have
but for
worked on
mechanochemistry, we use
submerged system.
for
This is an
chemistry,
example of a submerged
pharmaceutical.
system
And
for the
in terms
production
of
of enzyme.
solvent use, mechanical alloying
Lipase
typically
particularly
using the process with a
some
dry
of the medium
environment,
composition
but with
and some of the
mechanochemistry,
cultivation
we use
condition
often
from many
solvent,
organisms, and this is one example
not
of
like
some example
chemical
that have
synthesis.
put in this slides is actually from
So,
Chimicola laniginosa, from Aspergillus
next, I will
niger, and
introduce
also
on
from
what we have
Geobacillus
done in UMK
thermodenitrificans, which is
on alumina titania system, nanocomposite, prepared by
producing
HEBM for
thermophilic
coating application. So why we choose alumina titania? Because of the mechanical and thermal properties. Alumina titania composite can maintain hardness and strength
and
up
also
to 100 and
1100
degrees C,
surface
and also
methodology,
wear
and you can
resistance
see
compared
that
to micro
very little
composites.
variation between the predicted and
The
verified
role of
production
alumina
of the
here
enzyme. And this is
give the wear
example that you
resistance.
can see. Very
But
easy,
when we put in
on a
around
lab scale,
3
but the question
percentage
is how do
of
you transform
titania,
this into
it gives
production.
the
Another
it
process
gives the
is, as I was saying, is a solid state,
enhancement
a very
in terms
easy
of
process. You can do that in
insulation and
flask
wear
and
resistant
also on tray
coating.
system. And
So
again,
in the
you can
in this
optimize the
system,
system
alumina
because
titania,
microorganisms, I was
two
saying that
metric
is a
phases of
disadvantage
alumina
because
exist, gamma alumina
the
and
growth
alpha
of these
alumina.
organisms vary
And then for
with
role of
the
titania,
growth condition. And it is
titania
a primary
can be dispersed well
metabolic
with the
product
alumina grains. and helps
they are
inhibit agglomeration by partially embedding
close to the
into
growth.
alumina
Good growth
forms.
means good
And then
product
contributes to
production.
interlocking
And
the
as you can see,
microstructure,
in
then
the case
improves
of
the mechanical
in the solid state
integrity.
fermentation.
But if
Now,
using too much
again,
titania
as I was saying, there's a lot of
in
products that
the
you can come up with
alumina,
agriculture
they can
waste
lead
as a
the
substrate.
formation
You
of
can have
alumina titanate,
a
which then
blend of
affects
solid
the
state and submerged
densification, hardness, and
within the
elastic
same
modulus.
process for the production of, for example,
Okay,
fermentable
what is
sugars,
the
which is meant for
limitation
chemical
for the
industry.
alumina
And a
titania
lot of them are
nanocomposite to
used
be
for
used as
ethanol
coating?
production, for
When we
example.
apply with
Solid
thermal
state
spray,
and also some of the
alumina
enzymatic
titania
processes
often
and
leak
also physical processes
creating
for animal feed
warts,
formulation,
cracks,
which
and
originates from
delamination due
agricultural
to
waste,
agglomeration.
again through
So
solid
our
state
strategy
fermentation.
is to
There's a lot of
improve
research
the
to submerge
agglomeration of
fermentation
alumina
from
titania.
using
So
palm kernel and
we
also
focus on the
oil palm
using
waste and also
hybrid
palm oil itself
hybrid composite,
for yeast
meaning that
biomass
we
production.
put the
And
third,
these are meant, the
the
animal
third
feed are
oxide or
meant
the
for
third
poultry industry and
phases
also for
into the
aquaculture
alumina
industries.
titania.
Yeast biomass are meant for yeast
Okay, what we
extracts,
have
for
done
yeast
in UMK,
production,
we
and
produce
also
or synthesis alumina
formulated
titania
into,
with HEBM,
other processes.
and then we
within
produce alumina
manufacturing.
titanium graphite
There are
with
also
iron
nitrogenous
oxide, copper
compounds
oxide,
that
and
can also
HF.
be generated
Okay, this
using
is
local
generally the
agriculture waste and
method
through
used
SSF,
in
through solid
UMK.
state fermentation. You have
Okay,
composting,
so I will
product
introduce
compost,
one by
you have
one system
biofertilizers and
that we
also
have
elements that are
what
used
we
in
have done in
antibiotics.
UMK.
And
So we have
again,
milling time,
enzymes and flavoring
we
compounds
vary
are
the milling
also
time
products that can be
2, 4,
used
8, and
for
10,
solid state
and milling speed with 200,
fermentation. And
250,
you can
and
see
300 RPM.
these are large rooms, large
So
areas
what
for
the results
extensive research
we
for
get?
particularly in
We
research
found that
related
at lower milling time
scaling
for
up
300
processes, because
RPM,
this is one of the
there
challenges that we are
there
facing,
exists the metal
that we are
stable phase,
facing
which
in
is
terms of the
alumina titanate,
applications
but
of
disappears after
enzymes
8
and
hours
also
of
the
milling.
processes
Okay,
involved
after
in this
that,
application. Now,
after
this is an
sintering,
example of
okay, we perform
an
the sintering
optimized
after
condition
the
for solid state fermentation
milling
using palm
process.
kernel cake.
So after that,
One
there
of
are
the
no
substrate, palm kernel cake,
invisible of
one of the
the
substrate
alumina
used in solid
titanate
state
due to
fermentation,
phase
which
purity,
you'll
grain
find
size,
that
and environment.
they
But
have
for
to they looks
microstructure
good
evolution,
in
we
the
can
lab,
see that
but the
at
question is
10
how do you
a.m.
transform this
10
for mass
hours of
production?
milling,
Now, the tray
powders
fermenters and
become
the rotating
fine.
drum reactors are the two common types of bioreactors that
Okay,
are
next
normally
is alumina
reported in
titania
solid state
graphite
fermentation.
nanocomposite.
And
We
this is
vary
very
milling
important
time
because
for 8 and 10
the
with
enzymes
milling
are
speed
products
200,
that are used
250,
in
and
large
300
quantities,
RPM.
and you have to
Okay.
use in bulk.
So
So
we
if
can
under
conclude that
scale
from
condition, we are
the
not able to
SRD,
transform some of the application that are used particularly, for
there
example,
are
for feed, for
broadened
example.
peaks
You are
of
not
the
rearing just
alumina,
2 or 3
titania, and
chickens. You are
graphite,
going to have a
due
whole
to
squad
the
of chickens, and
deformation
there
that
needs a
creates
lot
the
of
huge amount
animal
of the
feed to work
defects,
on. Now, tray
which
and
can
tray
be seen
fermenters
from
and
the
rotating drum
reduction of
reactors
the
are two
crystalline size
important ones,
and
which
increase
we'll
in
look into
internal
this.
strain.
Now, in our laboratory, we have
And also
developed
we can
what
see
we
that
call
SEM
thermostat.
image, okay, not much
We have
different on
patented
the
this system.
in terms of
It is
the
an
microstructure.
SSF drum fermenter system,
Okay, and
which
then
can
alumina,
control
titania,
solid
copper
state
oxide,
fermentation
nano
under
composite.
many
We vary
conditions. So
milling
this is
time
the
with
setup.
2, 4, 8, and 24 hours.
We
With
can
milling
have a
speed
system
fixed
where
at
the
300
substrate is
RPM,
added
10.
Either batch, or in fact we can also use this on a continuous basis with all the air compressor for air control, flow meter. You have temperature control, you can in situ sterilization, you can sample, and also the whole system, which can also be aerated by agitation processes. Now, in detail of this structure, it looks complicated nevertheless, but it is a very simple process of translating the tray system, the drum system, into a unit which can involve a lot of substrate in kilograms, for example. This is the finding, that this is the setup that we have developed in the laboratory. Now, some more pictures of this. The most important, the substrate, because it's done spot, which is done continuously, and we can continuously sample it out for sampling, and also for continuous production of the substrate. at interval time that we have set up. Now, the agitation, we've got impeller to control, and the rate of agitation will determine the amount of moisture content in the system, and also the temperature within the system for maintaining the optimal condition of the fungus for the production of various kind of enzymes. Now, these are some of the results. For example, the xylanase production from Aspergillus niger and also from Trichoderma. One example is the substrate. You can change the substrate amount, you can vary the temperature, you can also vary the water content, and you can also change the agitation rate to suit which is the optimal condition which is meant for the production of the enzyme. Now, again, this is another one for other enzymes, mainly cellulases, CMC case, and also for FPase production by Aspergillus niger, USM-A1, and also from Trichoderma. And you will see that the production can be increased gradually, and this is done by controlling the firmstostat. Now, finally, that is the condition that we get for the production of the enzymes, cellulase particularly, and xylanase, which is then used for large scale application. This is the batch system, and which is repeated for large scale production. Now, as I was saying just now, we have also drum system, but we can also have the tray system, which is actually a we call it intelligent system because it can also control the tray system at each level, and you can have a control of this system at any level of the tray, and you can change the size of the volume to suit the volume of substrate that you need, and also the product that you expect to produce, the enzyme that you expect to produce from the system on the tray fermenter. Similarly, it has been used widely for the production and of many enzymes at the laboratory scale, and it will further translated with the help of the company within the country. Now, this system, drum system or the tray system, has been worked extensively, and we were able to produce varieties of various kind of enzymes which has partly gone commercial and tested for its application. You know, some of them includes lipase. One of them is lipoprotein lipase, which is used as diagnostic analysis, and others are used in fine chemical synthesis and also in detergency. We also have produced proteases, allergenic protein degradation in latex, and also feeds and detergency. Some of them, xylanases, hemicellulases, for example, they are used in enzymatic de-inking in paper recycling. I will talk about it later. We have cellulase in similar application as xylanase. Lignin peroxidase in dye decolorization has been applied in batik industry for decolorization of batik dyes. Manganese peroxidase, which is used in coupled with lignin peroxidase. Lacase, manganese, which has been done with the work with our collaborators at the Ministry of Fisheries on degradation of mannan in palm kernel cake for the production of fish feeds. Phytase is also for feed formulation for fish feeds, and last but not least, glucosidase for the fermentable sugar production. Now, if you look at the industrial application of this enzyme, the firstly I would like to share is on this, the application of lipase, lipolytic enzyme. Lipolytic enzyme is a wide range of enzymes ranging from lipases, lipoprotein lipases, and etc. There's a lot of esterases that are used, but particularly for industry application, largely it is lipases. And lipases works best for hydrolytic and also synthetic reaction. Now, if you can see, it is a reversible reaction. The hydrolysis in the presence of water, and the absence of water, you will have synthesis. But at the same time, the synthesis reaction can be can also undergo trans-esterification reaction, which comprise of basically alcoholysis, which involves alcohol group, acidolysis, the fatty groups, and the inter-esterification between two different esters. So this is the whole system, the enzymes that work, which we can actually capitalize and use that for industrial application. Now, the first figure that is in the slide is actually to show some of the hydrolytic impact. You see that if you hydrolyze an ester, you'll find that the varying production of triglycerides, diglycerides, and monoglycerides throughout the hydrolytic activity. And these are products that can be used for industrial application. As you can see, the reaction is controlled by water content. Without the water content, you'll find that the reaction is sort of unstable, and you'll find that there will be inconsistency in the degradation in the hydrolytic activity or esterification activity. But if you control the water, you'll find that the reaction can be maintained stably. Now, if you look at this reaction, the control of water is done by many ways, which I will then discuss in a short while, how you control the water in the reaction. And the table, you'll find that it's a reaction of esterification within different, using different alcohols for the synthesis of esters. Some of the example using lipases. Now, the product from this reaction includes fatty acids production as a result of hydrolysis. Fatty alcohols, you find that it is used in detergents, which is actually part of the product in the hydrolysis process. Esters, a lot of esters can be produced, and by trans-esterification, you can also change the acyl groups so that you can have structured esters that are used in cosmetic, lubricants, and also in plasticizers. Glycerin, mainly glycerol, as a product of hydrolysis. Methyl esters, soap, a lot of soaps from lipids, surfactant, lubricants, plasticizers, coating, and also food and feed additives as a source of oil and fats. So these are all oleochemicals. They come from natural oil and fats as the main product, as the main source. Now, this is an example of a product from that are used for the production of geranyl laurate. Geranyl laurate is used for perfume production as additives in perfume formulation, which can be done using lipase. And if you can see, it is done on a larger scale using bioreactor. This is a column bioreactor. And most important, as I was saying, it is actually done by controlling the water content. Now, you can position the arrangement of this bioreactor system by substrate addition in the first container, in the first chamber, and you can interchange the reaction by adding molecular sieve as a water control system, and also the column in the middle for the enzyme system. And in this case, the enzyme is immobilized on amberlite, which amberlite XAD7, which is used as the carrier for lipase immobilization. And you see that if you control the water, you'll find that the water content after the esterification reaction will increase. At low water content, the conversion is high, but as the water increases, the conversion starts to drop. And you can control at A, means to say that you pass through the column for water control, and you'll find that the conversion will improve back. And this can be done continuously over a long period of time, and you can maintain the conversion degree to close to about 90% conversion over a period of about a month. Now, another product is the acetone glycerol acyl ester, which we use as surfactant, monoacylglycerol, and it is also one of the products which you can use using isopropylene, glycerol, and fatty acids. And we use lipase from Pseudomonas species to produce isoacylglycerol with the product of water. but under mild hydrolysis, you can also obtain monoacid glycerol. And monoacid glycerol can also be produced by hydrolysis, but the quantity is not significant. Therefore, this would give a better conversion of close to about 60% to some, depending on the support material of the lipase used in the immobilization. But and with and wide specificity of carbon numbers that can use, you can change the substrate so that you can fix the fatty acids that you need for the monoacid glycerol. And this is done using organic solvent, inorganic solvent biocatalysis. I will also discuss something on organic solvent biocatalysis. And by changing the types of organic solvent, you'll find that it is also possible to change the conversion potential. And this is done on a continuous basis using a bioreactor system. Again, a column bioreactor system. And if you control the water subsequently using the control water system of molecular sieve, you'll find that the repeated use of amberlite X87, which is also used previously in geranyl laurate synthesis, you can go on for 56 days. This is in terms of because each cycle is actually for 24 hours of production with an 80% yield of conversion degree for monoacid glycerol production. Now, there are also organic synthesis that you can use with high EE using SSF material. You can prepare the SF material and completely use SS material as the source of enzyme, and we call this cell-bound enzyme, cell-bound lipase, the as a material, cell-bound lipase as an enzyme source in organic synthesis, and this has been done with reaction of conversion from 2-chlorine cyclohexanol to produce cycloacetate by introducing vinyl acetate in hexane. And this is the product that we are looking at, phenyl acetate, and this which is with high EE. And there's a lot of work has been done on this with various kind of strains and enzyme with different substrate, namely palm kernel cake, coconut waste. We use palm kernel waste, other palm kernel waste, which we with a good conversion for the formation of some of the material with high EEs, as indicated in these slides. All right. Apart from that, in the lipid industry, we use enzymes also to change the structure of the fats and oil. Now, one example, if you look at the table, you'll find the top table, you'll find that if you add beef tallow, for example, and olive oil, you can change the melting temperature of this fat, and it's a new structured triglycerides that is present within the fats because of the we call acyl migration of the between the glycerides that are present in the fats of, for example, beef tallow and also olive oil. And you can see that there's a reduction in melting point, and you can use this for industrial application. Now, the triglyceride composition also changed as they change the melting temperature, and these are very important because you can produce different kind of fats and oil using enzymes by changing the triglyceride composition. And at the same time, this another reaction which we use only stearate to introduce, which the degree or the amount of stearate incorporated will tell you the amount of C18 present in the fat, and they gives you a different level of fats. And some of them which can be used in food industry for certain purpose in the formulation, for example, in preparing products for lipid industries. Now, this is one. Those are in the lipids, fats and oil industry. Enzymes, alkaline lipase, for example, is also important in detergency. We have worked extensively in two organisms, Bacillus species, and another one in Pseudomonas posimobilis, which are used in detergency, formulate them, and this formulation of these are then comparable to the one available in the market. I show some example of the detergent that are used in our study to compare, and we find that the products are equally comparable, if not better, in terms of the detergents removal of dirts from fabrics with our formulation using crude lipase preparation. You can easily change the degree of dirt removal by changing some of the level of surfactant and also the level of enzyme concentration. Now, these enzymes are not just only used to remove dirt, but they also used to soften fabrics material. And now we've got other enzymes introduced in detergency. For example, cellulase. We have introduced cellulase into fabric, into detergents to actually soften the fabrics and also to create a texture in the finishing of fabrics upon cleaning the fabrics using these formulated detergents using enzymes preparations. One of the application in detergency as well, and other application that I like to mention before we proceed with the application, is actually on enzyme immobilization technology. Enzymes are immobilized because of the cost. Reason being because of the cost. It is important because we can reuse the enzyme. That is the main reason. To reduce the cost, you can reduce. At the same time, you can also stabilize the characteristics of the enzyme. You stabilize the conditions for the enzyme reaction, but also the most important thing is also to repeatedly use the immobilized system over a certain period of time. Now, the figure below shows one of the continuous hydrolysis by lipase, which has been using different immobilized system, which has shown to be repeatedly used for over a large period of time, over a longer period of time for hydrolysis, for example, in terms of this. And this is very important because we are meant to use it for industrial application. Now you can change the carriers, use either by entrapment, as shown in those figure, binding method of physical retention, either by binding to the carrier, cross-link, or even metric entrapment, or even membrane encapsulation. And you can see that the degree of hydrolysis varies. And again, if you control, as I was saying, the reaction, for example, by lipase, by changing the control system of the water system, for example, you should find that you will be able to continuously use the enzyme for a much longer period of time. Now, enzyme modification is another method for biocatalytic. Now, organic solvent, one of them is reverse micelles. Water in the oil microemulsion is one of those. These enzymes are very important because the hydrophobic nature of the organic solvent and also the aqueous nature, the hydrophilic nature. So you can trap the enzyme in the hydrophilic nature, but at the same time, the organic solvent can retain the substrate for the reaction to function. And this is what we call water in the oil microemulsion, which can be done using reverse micelle system, either using surfactant, various kind of surfactant that you can use in organic solvent. And these are some of the data that we have to show some of the level of the degree of conversion. There's another way to enhance further by modified with polyethylene glycol, the modified enzyme that we have, for example, with reverse micelles. But however, the reactivation of polyethylene glycol for this and lipase will cause some deactivation of an enzyme, which reduce some of the activity, but nevertheless, you'll find that the stability can be increased. For example, the half-life of PAG modified lipase is much higher than the reverse missile lipase, which is increased to 21 days instead of 8 days in the reverse missile. A lot of challenges through our studies. You'll find that for enzyme immobilization, if I were to go through this list, there's a long list here. I've got a few more minutes, I presume, but I've got still a few more, many more slides. But I'll try to speed up. Challenges, I can share the slides, so please read through the slides, and you'll find that some of the issues in enzyme application are uniformity and reproducibility. Scaling up, that is what I'm trying to stress. Scaling up is a very important issue and the most difficult part of the enzyme application work. So that is the thing that I think we challenge ourselves to work. Now, inorganic solvent is another area very important, because a lot of application for new products are actually not happening in the aqueous phase. They happens in organic phase. So there are a lot of organic reaction that you have to do, and furthermore, if you work enzyme in organic solvent, it allows for the enzyme to be reused, to recycle, because you can recover the enzyme. Now, organic solvent has characteristics that you can choose which organic solvent to work on. One of the characteristics is we call log P value. Now, for immobilized enzyme, we use aquaphilicity. Aquaphilicity is actually the ratio between water content of the carrier over water content in the organic solvent, and that goes what we meant by miscible organic solvent and non-water miscible organic solvent. So you have to choose. Now, normally the norm through our research work, we find that organic solvent with log P values of less than 2 is not suitable for enzyme biocatalysis, while the range between 2 and 4 is suitable. And log P values of organic solvent varies. And I put a table there ranging, for example, dodecane 6.6. The log P values is the ratio between solvent in octanol and also in water. You can use to measure the log P value. And formamide is relatively good in terms of, is low in terms of log P values, but it's not good for biocatalysis because it will give a lot of, it will have more hydrophilic in nature compared. So the ratio is about 2.2 to 4. Now that is the key, the thing that we look into. But you cannot use, you have to make sure that you can also control the water, because the hydrophilic and the hydrophobic nature of the organic solvent is also important for you to see that you have the right optimal condition for the reaction. Now, the two ways that we use to control the water in organic solvent is to use salt hydrates. Salt hydrates can provide an optimal hydrated enzymes. For example, hydrated with the numbers of molecule of water in the salt. You can provide that salt, that water for the enzyme reaction. So these are some of the reaction that we've done, and you can see that it provides a good source of water and nullify some of the water that are not necessary for the reaction. Now, besides that, this is some example also. You can work either in toluene, diisopropyl ether, or hexane. But you can, if salt hydrates is not suitable, we can also work with saturated salt solution. You can also use saturated salt solution because they also have different thermodynamic water activity, which you can also change the water activity within the reaction system for the enzyme. Okay, so saturated salt solution like lithium chloride, potassium acetate, potassium carbonate, sodium bromide, potassium iodide, sodium chloride, ammonium sulfate, potassium nitrate, potassium sulfate. All these have different water activity which will optimally hydrate your enzyme. Now, the use of saturated salt and salt hydrates for dehydrated enzyme can also be done. You know, enzymes which are deactivated because of low water can be reactivated if you use either salt hydrates or saturated salt solutions. And these are done either simultaneously, separately, and you can also dehydrate using enzyme, using just the enzyme or even just solvent, or also the substrate, and they will give you reactivation against the activity. Okay, very tense, you know. We got to control by time. Now, the carrier of immobilization also affect, I was saying, about the coaphelicity, but it is also important because you can use other ways to also strengthen immobilized enzyme. One of the example is in this case where you use calcium alginate, which is an entrapment process, but it can be activated using TMOS in and hexane, and this will help you to enhance the stability and also the conversion degree of the enzyme reaction. Now, that is so much of the enzyme in organic solvent. Now, I just would like to go very quickly on paper industry. This is another industry which we have been able to transform it into industry application. If I can have extra 5 minutes, Miss Moderator. Now, the paper industry is a very big industry, in fact, in Malaysia. But the most important, the one that is happening is in the recycling of waste paper is actually by conventional chemical methods. But we want to introduce the enzymatic method in paper industry. And this is important because it will help to the consideration of environmental impact that I've just mentioned previously. Now, the pulp and paper industry in Malaysia is very big, and you have something like paper import of 1.1 million metric ton per year, which is cost something to us. The paper that we use every day costs something like 2.7 billion a year for Malaysia. We use paper, and that's why we are moving towards paperless. But the only way that we use is actually from chemical method, but the recycling of waste paper that we use is only 5%. The rest are actually using chemical methods, and we are also running out of trees actually to produce those paper. But we are looking at Knaf as one of the source of paper in the industry. Now, the market is big, but we need a lot of industry. You are talking about tons of industry. Say, for example, 10 to 20 kilogram of enzyme is needed to produce 1 ton of paper. So this is an issue, like scaling up an issue even in paper industry. Now, so enzyme is the way forward. Now, de-inking involves dislodging of the ink particle from the surface, and then clean it up, remove the enzyme by suspending it, and then washing through flotation process. Now, it is safe, it is cheap, and using enzyme. And now, so the work is try to produce how to use enzyme in the de-inking process. So the majority of the work, most of the work is on the design, construct, fabricate enzyme bioreactors, and evaluate the enzyme performance in the de-inking process. So this is a lab scale when we started, and we managed to produce the flotation and enzyme process simultaneously with high quality paper production. And we come up with the optimal condition, laboratory enzymatic hydrolysis of the process. And with this process, we try to do scale up. And some of the characteristics of the paper, they are with the control, the one that is available in the market, we find that it's not very far different. You'll find that they are as equally good and has been used for use. One good thing is that we don't bleach the paper, because it is we don't use chemical, and we still have something like 95% brightness of the paper. Of course, the one after bleaching that they have is 99% paper, white paper. Now, based on that lab scale, we scale up. This is the schematic diagram of the pilot system for scaling up. We have the enzyme bioreactor for reaction of the pulp pulp from the waste paper, and we have the flotation to remove the ink from the paper that has been the enzyme. Now, the enzyme bioreactor, very quickly, the scale that we are talking about, we are talking about 150 liters estimated of 10 kilogram per run. So this is the study that we have done. Flotation system, we are talking about 750 liters for of the size for 10 kilogram of pulp has been de-enzymed the pulp to 1% pulp consistency, and this is then translated the schematic diagram with the help of the local company. So that's why I was saying it is important to work with the company. Otherwise, we won't come up with this kind of structure, because at the university, we're not able to do this. We work with the company, and there you go. We have got the structure, which is run on a continuous basis for the inking process. Now, some of the pictures to show some of the detailing of the setup. You have this pulp collecting vessels and so on. You have the control system, all those enzyme reactions and all the skimming process, and the agitation, the enzyme addition, and it's a continuous basis. The temperature control and so on. So this is basically how it looks like. We collect the pulp, and in this process, if you compare the chemical methods, they have a long process. On the two rights, it's actually from the literature review. It's a long process, but we managed to reduce it in a very simple method from the waste involving just the hydrolysis and just the flotation, and then we washed it, press it to produce the paper. This is the paper that we work on, office paper waste and the old newspaper. All right, and these are the conditions that we run: the temperature, the enzyme concentration, the surfactant for the flotation processes, and also the condition that the hydrolysis is done for both papers. MOW is for office waste, and old newspaper, OMP. You'll find that the characteristics are at par. Even after under continuous process. So last but not least, we managed to get after and before the enzymatic hydrolysis and flotation process, it is actually close to 95% brightness, which is now used by a local company to recycle some of the papers. Now, in environmental management, the big research grant is actually coming from Petronas that we've got to do on bioremediation of the spilled petroleum. But you know, environmental management, we use microorganisms and enzymes to actually do environmental management. I'm not going to go through the detail. We have used a lot of these enzymes and microorganisms to do bioremediation work. It is important, and some of the enzymes that are used is actually hydrolytic enzymes. There are a lot of oxidoreductases and other enzymes that are also used, like ligninases, particularly lignin peroxidase and manganese peroxidase, and also chitinases, and which improves the degradation processes and also the remediation processes. And one of the studies that we also have done is through the Ministry of Perumahan Kerajaan Tempatan, Housing Ministry, is on try to put decomposing setup in flats. You know, that is a setup that we have created to actually help people with domestic waste decomposition, and we produce inoculum for them, and we also produce a door absorber which will help to reduce the smell throughout the fermentation process in household. And this household waste is actually waste from the kitchen that you use it, and then you try to process it, and you dry it, and you can throw the dried form of the waste, which can use as feeds for animal feed, and you can also dispose as waste very systematically. And this has also been translated into application. Now, the other application related to enzyme is actually for environmental application is in our batik industry. I work closely with batik industry in Kelantan, particularly for lignin peroxidase and manganese peroxidase to actually clean the waste generated from batik industry. And this is the picture from a batik company which is now has closed in Pekalan Cepa. We have, but unfortunately, batik industry like this is is a small scale. They cannot afford to use technology like enzyme technology, you know, to solve the problem. So we have that bottleneck, but it is working, and it can be used very effectively. So we propose this system to the ministry to actually look into how we can solve the problem to be fixed at the factories of batik for decolorization using enzymes from Phenolricate chrysosporium, an organism that is producing lipase peroxidase, lignin peroxidase, and also manganese peroxidase. Now, in agriculture, there's a lot of work. There's a lot of things in the production, in the enzyme application. One is the compost, and the other one is we use it in animal feed industry. This is a research that we have done to include phosphatase, hydrogenases, and also urease to improve the application, to improve the soil fertility. We also work on other products, some of the agricultural waste for fermentable sugars, and these fermentable sugars are then used for production of a lot of other products, namely like candida, for fish feeds, and also for production of a product called astaxanthin. Astaxanthin is a red pigment. In the slides, you can see there's a fermenter which contains astaxanthin, which is in the process of production. And bioethanol is one of those. Now, this is the slide for bioethanol production. Very important. It is workable, but the economic of scale is still a question that need to be addressed. Now, animal feeds a very big industry. We have been able to work with the poultry industry and also with fish industry, aqua feed, to produce from animal feed, particularly with PKC. A number of our graduate students, postgraduate. We've got one from UMK graduated, the first PhD in science to graduate with work on aqua feed industry using PKC, and this one is for poultry industry. For medical application, a lot of enzymes are used. We don't work very much on this area, but we know very well there's a lot of areas that can be done in medical application. You know, it is also important that enzymes can be used to diagnose disorder, and these are some of the application, including the enzymes used for formulations in toothpaste. All right, but for us, we work on analysis. We work with Caldinhamella acuminata, which is used for triglycerides, lipoprotein lipase from this organism to actually determine the total cholesterol in the serum using cholesterol oxidase and cholesterol esterase obtained from Caldinhamella acuminata. And this is it's either using chromatographic or also using chromatographic dips. As you can see, it is if you compare to the commercial diagnostic kit, triglycerides is available from Abbott Laboratories. We find there's no significant differences at the confidence level of 0.05% in the use of enzymes from Caldinhamella acuminata. Now, biosensor can be translated from that diagnostic kit, which actually by the help of transducer, which is translated thereafter based on the enzyme reaction. There is a difference between the diagnostic kit that we use based on chromatographic methods. In pharmaceutical and cosmetic industry, yes, there's also a lot of application. Read it slowly. Food and beverages, I've taught a lot on lipase application. There's also a lot of enzymes that are used in food, particularly in fat industry, but also in the production of functional foods. In nanotechnology, we have got nanozymes. Nanozymes as a nanomaterial that exhibit enzyme-like catalytic activity. But there are also nanomaterial that can be used as carrier for enzyme immobilization that we can use as nanozymes as well. this is a long story, a lot of work that still need to be done, and I want to wish good luck to my the researcher at FPKT so that they look into this also, enzymes and nanotechnology. And I have got not much time to work on this. I have to leave the university at that time, so I would love to see the new things in this area in the future. Now, last but not least, I just like to mention that the way forward is enzyme engineering. Now, protein engineering, as we call it, it is actually you can change the structure of the enzyme to suit the needs. This is basically to increase the thermostability, to change the enzyme reaction so that it is more stable, it is more useful. You can also change the kinetic properties of the enzyme. You can also change the enzyme configuration and structure to suit, and it can easily be used to suit up the application that we need to do. For example, by changing the sequence of amino acids on the enzyme protein will also allow the enzyme to change its function and its applicability. Now, one example, for example, when I say change the role of the amino acids, we can do this chemically. This is one example. For example, if I take the lipase from Humicola landigenosa, you'll find that the active amino acids that is functioning is actually coming from tryptophan. You can control the amino acid tryptophan in the biocatalytic activity and see which part of tryptophan it is actually important for the biocatalysis of the enzyme. So if you can control that tryptophan, then you will be able to see that you can also enhance the catalytic of the activity. And this is one of the examples that we have done to control the tryptophan role. And we discover that the significant role of the tryptophan is the residue number 7, which is present in the all phase of the biphasic reaction phase of a particular lipase. So this is one example that I like to share. But there's a lot more that you can do, and people are doing protein chemistry. There's a lot of protein chemistry that are done to actually change the amino acids of the enzyme. Now, last but not least, this is the last slide. I think to do work in the future that we are looking at. I'm talking about a lot about process engineering, about process of producing the enzyme, process of trying to translate the reaction of the enzyme. You know, there's a lot of work that's been done. Although the scaling up is a problem, but there's also enzyme engineering. I've just mentioned about it. But most important is also biocatalysis, because if you can suit biocatalysis and enzyme engineering and protein engineering, therefore you can also make it a lot of adjustment to actually improve the process engineering, and this can be done to scale up the difficult part of the processing and also the downstream processing. So these are the 3 areas that I think it is important, which we have to look into the enzyme engineering process. And last but not least, to conclude the presentation, I still feel that the major constraint for enzyme work is actually the large scale application, and this is also coupled with stringent regulatory guidelines for manufacturers, especially into safeguard the human consumption, particularly in food industry, such as, for example, in halal certification. I'm not saying that halal certification is giving constraint, but we have to oblige to this, and there's some obstacle that it is important. The commercial enzyme catalysis is feasible, but if you can overcome some of the economic problems, because some of the process are feasible, but they are not economically possible. Great challenges in the natural substitute for synthetic chemical, and this leads to the application of enzymes. So it is inevitable that you have to look into enzyme application. Future research in enzyme technology will have to focus on novel enzymes. It can be the same old enzyme, but with new structure, with new configuration. But last but not least, you have to help the country. Do not allow Malaysia to rely strongly on imports of enzyme, because there are a lot of research around the country on enzyme production, but the translation for scale up production of enzyme is still limited, and we need a lot of support from the industry to make sure that they can produce industry in large scale, and therefore we will be able to use it on a large volume. So thank you once again. Thank you once again for the organizing committee. Thank you particularly at BKT for allowing me to give a talk on this topic. I know there's a lot of people who may have questions, but accordingly, my point is we still have to work a lot more to be able to answer a lot more questions in the near future. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh. Thank you.
Okay, thank you, Yang Berbahagia Datuk. So your sharing today has given us a deeper understanding, definitely, on impactful advancement and future direction in the field of industrial biotechnology, as well as the invaluable connection between research, innovation, and practical applications. Your wealth of experience and contribution both in Malaysia and internationally are truly a source of inspiration to all of us in the scientific and academic communities. So we are unlucky today due to the limited time. We are not able to proceed with the Q&A session. So I think if Datuk can maybe jot down your email in the chat box.
Sure.
So if anybody got any questions, you guys just email Datuk personally.
Sure.
For any queries.
Yeah.
So Datuk, on behalf of the organizing committee of Iconbet 2025 and all participants here today, we extend our heartfelt appreciation for your time, wisdom, and continued dedication to advancing science and education. Please join me once again in thanking Professor Datuk Dr. Ibrahim Cik Omar for that insightful and inspiring plenary lecture. Thank you once again, Datuk.
Thank you. Welcome.
Okay, with the end of the plenary lecture, we are now come to another slot of this afternoon session, which is the invited talk session. So it is an honor for me to introduce our invited speaker, Dr. Alan Wong, the Technical Manager at InnoLab Engineering, Sendirian Berhad, which is also a valued sponsor of Iconbet 2025. So let me give a brief introduction on Dr. Alan Wong before his presentation. So Dr. Wong has over 6 years of experience in advanced material characterization with expertise in X-ray diffraction or XRD, X-ray fluorescence or XRF, and also matte flow index analysis and universal testing systems. Today, he will be sharing insight into Bruker's extended range of X-ray analytical solution, highlighting state-of-the-art techniques and technologies for advanced material research and industrial application. Please join me in welcoming Dr. Alan Wong to deliver his talk. And Dr. Alan, just a gentle reminder, you have 30 minutes for the presentation, including the Q&A session. So Dr. Alan, I pass the session to you.
Okay. Good afternoon, everyone. So I'm Alan. I'm a technical manager in InnoLab Engineering. Is my sound okay? The voice?
Okay. Yes, doctor, we can hear you clearly.
Okay. So today I will talk about generally is the tentative. So I will talk a little bit about Bruker analytical X-ray solutions, why we use X-ray fluorescence spectrometry, why we use X-ray diffraction, and also a little bit about X-ray microscopy. So in general, Bruker Corporation is a large group. So what we focus today is more on Bruker analytical X-ray solution, which involve XRF, XRD, and X-ray microscopy. So in Malaysia, we have a production plant in Penang, and also lab application in Singapore. So these are the picture of the location of the production sites. So today we'll focus more on the analytical methods. So in X-ray products, we have divided into 3 analytical methods. One is structural analysis, which we get the structure of the materials in an atomic or molecular way, either by XRD, single crystal, or even through if connected with SEM, we call it EBSD. For elemental analysis, we have XRF, and we have different type of XRF depend on customer requirement. And we also have the electron microscope analyzers like EDS, WDS, and also micro XRF. And in terms of 3D imaging, we have X-ray microscopy. Totally, we have a huge extended range of X-ray analysis solutions. Lab to really high throughput dedicated for lab or R&D analysis. And also our analysis can be differentiated based on spot or bulk analysis, or we can go to higher like mapping analysis where we want to see the distribution either by elemental or by phases. So, and we serve wide range of industry and academia, whether in food, petrochemistry, cement industries, batteries, semiconductors. So now I will start my focus today on XRF, X-ray fluorescence spectrometry. So I believe probably most of the group today know what is XRF. So just a refresh, X-ray fluorescence, short form is XRF. It is an elemental technique. So it determines either relative or absolute concentration of elements in a sample. It don't give any molecular or crystal structure of a material. It also won't inform you what is the valence of an element. It won't tell you what is the isotopic composition. For those that are new to XRF, generally how it works is that we use X-ray to shine on the sample, and the innermost shell of the electron will absorb this energy, and it will be emitted from the innermost shell, and there is a vacancy here. Normally, the nearest shell of the electron will fall into this empty shell or vacancy shell, and in the process, they will emit, we call it either a photon, or we call it like fluorescence X-rays. So these fluorescence X-rays, I would like to highlight is that have both energy and also wavelength properties, and this is characteristic for each element and its atomic structure. So either this energy or this wavelength, this will be measured with a detector, with 2 types of detector, either by wavelength dispersive spectrometers or by energy dispersive spectrometers. Okay. So we start with energy dispersive XRF. So generally, we call it a high throughput silicon drift detectors. It has these detectors, which will capture entire energy spectrum. So this is normally used for unknown sample, which is very good because we will generally get the whole spectrum of the elements. And it does not need any analyzer crystal, and sometimes it may have those beam collimators or filters just to optimize the beam conditions. So this technique is very good to get short analysis time compared to wavelength dispersive XRF. And customer does not need to know like what is the elements in advance in order to run this test. And this, if you see based on the spectrum, normally it has poorer peak resolution compared with wavelength dispersive. So the software will have greater reliance on, if let's say there is a peak, nearby peak, so based on the software, we call it deconvolution, or the software how smart it is to deconvolute these overlaps, and they will give you the elemental concentration. So this is generally how the XRF set up. You have an X-ray tube, your sample will be here, and you have a detector. So generally, what you can see in the market, you have the portable ED-XRF, you have the benchtop, and there's also other technique like micro XRF or even the total reflectance XRF, which is normally used for liquid. All of these are using energy dispersive XRF technology. And we move on to the wavelength dispersive XRF. So different is that it has one analyzer crystal in between before it, after it reaches your sample. This analyzer crystal normally is rotated to diffract the X-rays so that towards the detector. So this normally for generally at least 3 crystal will be inside wavelength dispersive XRF. This crystal is used to optimize different diffraction of these different wavelength of the elements. So, and this WD XRF is generally have 2 types. One is we focus on sequential. So sequential means that it can only measure one element at a time because it will be focused by one crystal and then it will collect by a specific detector one at a time. And this is, so you have more elements, you will take longer time compared to when you just measure for one element. So normally in the market, broker have this benchtop model and also the floor model as well. And in terms of simultaneous, we also offer have this model, but this is mostly in industrial where they need it fast. So, and it's much more expensive because each element has its own detector. So we have a model for this, we call it Lion. So what is the benefit of this wavelength dispersive is that if, so on the screen on the right, so we can see a difference of the peak of the spectrum if we compare with the wavelength dispersive and also ED-XRF. So in the wavelength dispersive, you generally have a better peak resolution and also signal to noise ratio, which allows a lower limit of detection and better precision as well. So a rule of thumb probably like if you like WD-XRF generally it can go down to like single-digit ppm, while wavelength, while energy dispersive generally is good probably around hundreds of ppm and above. So this is the range of elemental concentration, generally the limits. And if we WD-XRF is we consider it as a very versatile application because it has additional filters and crystals and how to control the beam. So generally it can be applied for all industries. The only drawback is that it's only customer need to know what element they want to measure in advance before they use this instrument, because most of the instrument they are dedicated single elements. We call it single X-ray, single elements or fixed X-rays. And generally WDA-XRF also is not optimized for element mapping. And this year, to counter this single element drawbacks, so Brooker has a new model called SA Tiger Series 3 where it combines both WD-XRF user, and if let's say you have some elements that is you do not know what is the element and you know generally the element is in percentage or is in high ppm, then it can also add additional ED, we call it multi-channel or ED energy detector onto the WD-XRF for faster analysis. And also for WD-XRF user, they can also analyze unknown sample. For WD and also ED-XRF, generally Brooker, we provide like pre-configured elemental solutions for different industries. So these different industries generally separate into like geology, cement, metal, petroleum, or even polymer. So we provide generally what we can say like a common range of certified reference material to perform the calibration. And we will use that calibration as a base to get the concentration of the material that is analyzed. So normally this standards is compliant to either ISO or ASTM international standards. So we move on to the application. So for today I'm probably more focused on the geoscience. So this how does this elemental analysis in geoscience generally the characterization of this elemental composition in geology is very important either for research or industrial applications because it provides information on what is the rock type, or we call it lithology, or what is the alterations or the special difference we call it the scales of the rocks, and also what is the minerals and their compositions. By understanding this elemental information, we will get an idea like how is the geological processes, whether how is the prospectivity and the economics of this ore deposit, whether it's worth it to mine or not worth it to mine, and also how does the environmental impacts of waste for this area as well. So because we have a lot of products, a range of X-ray solutions, so how do I choose and when? So I have separate my slides according like how shall we select either the samples or the instrument when we analyze the material. So first we focus on the instruments. So generally in the market, the instrument for XRF generally divide into two types. One we call it bulk measurement analysis. Another we call it fine scale measurements. For those that are normally in soil or in geology, probably to give you a better idea is that fine scale measurement, probably you can picture it like something you measure in an SEM, where you measure in a very fine scale, whether in a nanometer or even picometer. But for XRF, we can go down to microns. And for bulk measurements, generally, which is conventional XRF we are doing, which we generally measure a spot of your sample and we average over the area of the spot. So for bulk measurement, if let's say the instrument generally focus on bulk measurement, the sample required must be representative. So because the result will depend on the homogeneity of the sample. For the fine scale measurements, generally, we just need a flat or kind of flat surface, and we just can run the sample and we will know what is the distributions of the elements or the mineral, we call it mineral zoning. And then we move on to the sample type, because sample in the ground can be varies depend on industry or field application. So when we look at the sample, if you see on the picture, so we need to know like how does the sample change, whether does it change its color or change its how it looks like in meters, like this in meters or in centimeters, or we look at the centimeters or even millimeters or in microns. So this will we call it this scale of heterogeneity, where this will determine how we want to analyze this kind of sample. And this material composition normally is different when we measure metals or crystals and even polymers. So we can see if let's say we talk about and all of this, if let's say we want to see how heterogeneity is, we can just make a scan and we can see the distribution. Like for example, in the picture on the right, we can see how is the distribution of the elements accordingly. And besides the scale of the instrument and scale of the sample, we also need to think of what is the goal of the measurements. Like you measure what is the purpose when you do measurements. So one of the common one is you want to have a representative measurements. So normally we do this, for example, whether we can we do this go, for example, you are in have a drill core sample, we separate according to the intercepts, or we base on block controls where we separate based on the grade and we analyze it, or we can base on the weight of the numbers to define the pattern. For example, for soil sample, we can also separate based on the location, and we block it out and we collect it and analyze and based on the soil sampling plan. And another goal, normally, if you have high sample volumes, then you will be more targeted on the instrument that can provide quick measurements. But in order to, for XRF, if, let's say we want to have a quick measurements, generally either you use a EDA XRF or you know what elements that you are interested in and we only targeted for that instrument, like for the elements. Then it will be this measurement, you will get a faster, shorter time. And another goal generally used for XRF is like we have geologists or even site that want to know how is a deposit is formed, or we call it like geology term, they call it paragenesis, but simple term, we want to know like how does a deposit is formed. For example, this is a picture of a porphyry. So generally, this is normally seen is used like for decorations. So if let's say you are interested on a high precision concentrations, then a good advice you probably just crush this. For example, crush this specimen and powderize, and straight away we analyze it with WD-XRF. But this, when you're doing this, yes, you will get a very good concentration, but we will lose all mineral compositional relationship about how this deposit is formed. So we do have another technique, we call it micro XRF, which will map out this information. So for example, these are the image that we review. It will be reviewed. If let's say you want to know how this deposit is formed, so on. Some of the information, just briefly I want to show is that, for example, on the top right, the potassium, this blue color alterations, and the veins here is together. So we can have this relationship as well. And another relationship, for example, at this bottom image is that we can also see that, for example, copper, which is in blue, they are not related to this vein at all. So these are some of the simple information. There are more information that can be deduced depending on the sample itself. So generally, we would like to know the relationship of this mineralogy because generally one is to know how does the sample is present and how does the mineral generally composition by looking at the let's say it exists together, then they are together. And another time, this is very important. If let's say you are doing processing, mineral processing, we also can, this image will show you how is the mineral department, or how does this all minerals that occur relative to one another. And the picture on the right will show like the distribution of this element. So for example, on the top for cobalt, so the red color means that it's high concentration, and the blue color means that it's very little or almost none. Black is none. So this is a general picture on a rock. Like you can get like copper, cobalt, arsenic, nickel, and silver. This is an example. And another example, if we look at the mineralogy of soil, stream sediments, or heavy mineral concentrates, generally we can, by a simple screening, we also can find we call it indicator minerals. Like for example, if let's say we find silica, most likely it will be quartz or plagioclase. If we find ethium, most likely it related to xenotime example, or cerium, it will related to monazite. Zirconium, and it will be related to zircon. And also sometimes through this image, we also can get the size and the shape criteria of these elements. And the last parameter will be based on the field-based investigation, on the what kind of setting you are probably would like to test it. If let's say you are in the field-based investigation, like you are joining outcrop-based studies, or you want to have a rapid screening, or in situ soil surveys, or even like core logging. So generally, you will get to see is that, so this core, it will be different according to the depth. So generally, portable unit will be the best to measure this kind of sample. And if let's say you are in a plan to analyze for grade control, process monitoring, and it's for short-term projects, then probably a benchtop will be more ideal. And because benchtop also can provide a lab-grade results. And lastly, if let's say it's dedicated laboratory setup, then a flow model will be more recommended because it has high sample volumes. And there's also, for industry, there is always a potential for automations. So these are some of the WD-XRF and also XRD that used with automations. Okay, then we move on to X-ray diffractions. So what is X-ray diffractions? Normally, this technique, generally we use it for structural analysis. So how it works is we use a low energy X-ray beam to illuminate the sample. And each sample has its own molecular arrangement in the sample. And this creates a unique diffraction pattern, which will be scanned by the detector. Generally, this kind of, we call it diffractogram, will be saved in a database, or we compare with a database. So what key information normally we look on is normally three things, which is the peak locations, the peak shapes, and also the relative intensities. So software will process this pattern and determine the informations about what is the properties of the material when they compare with the database. So what are the information is, we can get the crystalline phase composition, crystal structure, crystalline size, strength, stress, or any defects, layer thickness, textures, and also chemical composition. And we also have a variety, different kind of XRD. So generally, if you already know what you will analyze daily, normally we will just recommend the DA Endeavor normally used in industry, because they always analyze the same molecule or compound or same type. But for research or for unknown sample, normally depends on how complex it is. So generally, it will be these three models. So why does this mineralogy matter? Why XRD is important? So generally, if let's say for minerals and mining, normally they only get the element concentration, mostly is already enough, because this is a very well-established method for generally to analyze the element, and this is they normally measure it either by XRF, OES, or even MS, like ICP-MS as well. So but when we get this element information, sometimes we do, based on the element, we do not know the physical properties of the minerals, because the physical properties of the minerals mostly depends on how is this atom arranged. Probably some expert, probably they can just know by seeing the composition of the elements. Maybe they can deduce like what kind of mineral is that. But most of the time, like person that is new to the field, they're unable to straight away to know what is the physical properties of the minerals. So in this case, XRD is a good instrument to help to identify what is the mineral phase of the sample, and also can measure the concentration based on the phases. Knowing this kind of minerals or phases is very critical, especially on the financial impact, because one, based on the XRD, you will get what is the economic value of the material. And because generally elements do not exist by itself, it need to be processed. So by knowing the minerals, we also can calculate what is the cost of mining, transport, and how easy it is to be processed. And this processing cost normally also involve like beneficiation condition and cost as well. And with XRD, it also is used to control the grades of the minerals, like how much of the targeted mineral grades that we can recover. So for example, if you look at for example, in an iron ore industry, for example, so normally how they control the grade and the impurity control is by using XRD. So normally this is very important, because the profitability often is influenced by the close control of these grades. So generally we will target the highest grades of iron ore, and also because these are the grades that makes the most profit. And then by using XRD to track the recoveries of these iron grades, this will also minimize the impurities of the iron ore as well. And besides tracking the grades, we also track the iron ore valence, like whether it's iron 2 or iron 3. Or so on the right, you will see generally these are the three most common iron minerals, like hematite, goethite, magnetite. So different kind of valence will determine how much is the reducing agent needed. For example, in the steel product for the steel production. So this will affect the cost and also carbon footprint. Another thing, another industry we can see is probably like copper, when they mine for ore, and also the mineral of the gangue. So So generally they use the XRD one. They will target the mineral species and the grades and the recovery rates. These are the most common use of XRD. By knowing this, then they will try to control the moderate energy consumption at the mill. And XRD is also used to predict what is the minerals that will influence, for example, the acid usage, or whether if let's say it will be used in the clay, then they will have flotation behavior. And it also can reduce waste generation by predicting what is the potential acid generators that is heading to the waste path. So if let's say we look at another application, for example, is in like bauxite. So normally bauxite is a kind of mineral mixture where it contains aluminum oxide and also hydroxides. And generally, aluminum occur in one of the iron phases, we call it goethite. And generally, if we use XRF, we generally tend to overestimate the recoverable aluminum. And this can sometimes be cost up to 10 million per year. So because this goethite, most of the process for recovery used for bauxite industry, they call it bio process. And most of this time, the iron, if let's say the iron is if let's say this goethite is high, and roughly it's about 30% of the iron in this goethite is not recoverable based on this process. So if you are using XRD, this will provide a good estimate of the aluminum they're able to recover. So we move on to probably these are the last X-rays solution that I would like to share, which is 3D X-ray microscopy. So generally, this is a technique that generally something if let's say in the medical field we call it like micro-CT, but in a material field we call it more like compared to a traditional microscope, but we analyze it using X-ray in a 3D view. So this technique we can measure it either by reflection and also transmissions. And it generally can put any kind of sample inside. So what kind of information that generally we can get from this analysis technique is that, for example, if we put a rock, then we can find what is the pores or the cracks, what is the mineral distribution, shape and sizes, and what is the API distribution, what is the coatings, and also is there any inhomogeneities and defects. And also we also can conduct in situ and non-IBM inside this 3D microscopy. So these are the examples. I will show you how this works. I will share a video about this. Okay. Okay. So that is all from me. I'm open to Q&A.
Okay, thank you very much, Dr. Alan Wong, for the informative and engaging presentation on Bruker's extended range of X-ray analytical solution. We have one question in the chat box.
Oh, okay.
So normally, REE often occur in trace amount in natural, which is below the detection limit. So how XRD and XRF may overcome this problem?
Oh, okay. Okay. So generally, in the field, for example, this is just an example. So for example, REE, if let's say it will occur in trace. Generally, most of the site will be occur in trace. If we let's say measure by traditional technique, like for example, if we plan to measure like normal soil in a WD XRF or even the ED XRF, straight away I will inform you that the normal ED XRF will have difficulty of detecting these traces. But probably they need to go for wavelength dispersive. But even wavelength dispersive also sometimes very difficult, depend on the concentration. Generally, because of the traditional technique that we use currently, which is we crush, like we collect maybe, for example, maybe some of the sample we crush and mill it. So generally, for example, if let's say the original concentration, like original grain, maybe it's like normally original grain they have maybe is like most of the time will be like more than hundreds of ppm. If let's say in a grain size, but if when it is crushed, this 100 ppm or more of this will be when it's divided across a cross section area. This most of the time will be lost. Like because it's probably when it's crushed, it can go down to ppb or even single digit ppm level, which cause generally researchers or professors use, instead of using XRF, they go for ICP because it's too low. So this is what is the common solution that I can see. But if let's say with one new technique which I can probably offer, like if let's say you just want to know like to find where is like generally to allocate where is the rare earth easily. So probably another technique I can show is, for example, without crushing the sample, you just like a sand, you just draw it, like just pour onto the location, and we can measure this in a micro XRF. So in a micro XRF, generally we don't see as an area. Because if we see as an area, then we very hardly to detect this element. Because without crushing the generally, like for example, this cerium, we can see this cerium is only located like this or these 2 grains only. You can see, if let's say you see this picture, so you can see these green grains actually they are not a lot, but we can detect it because without crushing, they appear in, I can say like at least 50 ppm or above in grain alone, when it's in grain before you go to milling or you go for crushing. And with this technique, you can actually find whether there exists any rare earth there. And when you want to do quantitative, we call it quantitative measurement, only you go for either a WD XRF or even for ICP, MS, or OES. But if let's say it's for exploration, or you want to know whether the area, because you are looking for traces, this is, I can say, is the easiest technique is using micro XRF. If let's say you want to know where it is, because if not, then if we straight away crush this and move to ICP or even WD XRF, generally I can see if let's say the site generally in high ppm level or percentage level, only you will get easily find out the concentration. If not, you will get probably only the ICP, MS, or OES can give you the ppb level of quantification. Yeah. Do I answer your question? Because if you just want to look, yeah.
Okay, thank you, Dr. Ellen, for the answer. Okay, so based on your presentation just now, is the characterization is more focusing on the minerals, right? So my questions, this machine, is it applicable for biological sample? And if it's, yeah, is it applicable, can be used for characterization of biological sample?
Okay. Yes, it can be used for biological sample, but as I mentioned, because this is an X-ray solutions, if let's say a biological solution, because I'm not sure what you mean by biological solution, means that anything that we tested, it will be undergo X-ray. If it's a live material, generally after the testing, even though it didn't die, it will die eventually.
I see.
Yeah, so we do have this test for biological, maybe like leaf, fish, or even, yes, we do. This can be tested on this technique. It's just that like even like strawberries or fruits, we can see the distribution of the nutrients based on the soil we feed or based on the fertilizer, where does it grow. This information is we able to see it with this technique. Yeah, so it can be used for biology, but only for elemental base. If let's say we talk about XRF. And
we have one more question here. How about REE containing glass, gel, or disordered phase, which is the amorphous? Is current XRD still cannot be used for characterization?
If you mean for gel, REE in gel, but I cannot straight away say no, because this is always depends on the one. It depends on the library. Another one, the gel is we always depends on the how is the because generally the diffractogram will be amorphous if we talk about this kind of material, and this kind of material normally we need to XRD able to differentiate this, but normally we need to make like some sort of simple calibration in XRD in order to quantify this type of material. Yeah.
Okay, I hope all the answers.
If you can also email me, or
sure.
I'm not sure how.
Maybe Dr. Ellen can just jot down your email in the chat box. So those who has inquiries then can personally contact Dr. Ellen for the inquiries. Okay, so thank you again, Dr. Ellen. So your talk has provided valuable insights into the latest advancement in X-ray technology and the application across research and industry. And the practical knowledge you've shared today will certainly benefit many of us in the bioengineering and material science communities. So on behalf of the organizing committee, we would like to also take this opportunity to extend our sincere appreciation to InnoLab Engineering Sdn Bhd for their support as one of the sponsor of Iconbet 2025. And once again, please join me in thanking Dr. Alan Wong for his talk and also his contribution to this conference. Thank you again, Doctor.
Thank you.
Okay, with the end of the talk from Dr. Alan, we are now come to the third slot of our session this afternoon, which is the oral presentation for energy technology. So we have two speakers, Dr. Fazilah Hashim and also Dr. Ahmad Zul Izi. I hope both presenters are ready. Okay, without further ado, I would like to invite the first presenter, Dr. Fazilah binti Hashim, with her presentation. InnoSat attitude control performance comparison using PID lead, MPC lead, and MPC PD lead controllers with the effect of varying gains. Once again, I would like to remind the time allocation is 10 minutes for the presentation and 5 minutes for Q&A session. So the floor is yours, Dr. Fazila. Can proceed with your presentation.
I should show my own slide. Yes, I have to show my own
please share your slide, your screen.
Yeah. I'm not sure that I'm.
Okay, we can see your slide, but it's not the front page.
The front page. Okay. I don't know how to put my slide.
Okay, we can see your slide.
You can see my slide?
Yes.
Okay. Okay, Assalamualaikum and good afternoon. My name is Fadilah binti Hashim from Polytechnic Tuanku Sultanah Bahiyah Kulim Kedah. I will present my paperwork with the title InnoSat Attitude Control Performance Comparison using PID lead, MPC lead, MPC PD lead controllers with the effect of varying gain. Okay, here is the authors involved in this paperwork. The first is myself, Dr. Fadilah Hashim, and then my colleagues, Mrs. Munirah Nujid, Professor Madya Dr. Siti Mariam Sharon, and Professor Dr. Muhammad Yusuf Manshur and Ms. Nur Hidayah Zainal. Okay, for the introduction, we can see from the slide, from the upper left side, this is the standard, the standard of cube set size. The first one is 1U, but in this paperwork, we use 3D. We use 3D, 3U. This means 3 unit of the cube set. Okay. And then the upper middle shows the external view of the InnoSat. Okay. And for the right side shows a block diagram of CubeSat subsystem. Okay. And we know that the cost of the small satellite for research has increased recently due to their size, design, development, and power consumption. Consequently, it is rather cheap. Inexpensive. It's now possible to create small satellite for everyday usage and research because of rapid technical breakthrough. Also, there are various categories for mini satellites. The satellites are differentiate from each other based on their weight and size. And we have the agency, the National Space Agency, Angkasa, in Malaysia, that creates the innovative satellite. What we can call it InnoSat, is a type of nano satellite to stimulate interest in satellite building among Malaysian institutions. Okay. Here is the methodology. From the left side, these are the equation. This is the transfer function, which is represent roll, pitch, and yaw axis. We can see it as equation number 1, 2, and 3. And then all of these equations should be converted into equation 4 and 5 here. And on the right side, this flowchart shows the step to design and simulate the controllers. Okay, the process starts with the design and development of the InnoSat attitude controls. And then, which is based on the state space approach, then construct the MATLAB code for the simulation. And next, we check the performance. If the controller is okay, then we can compare all the controllers. If not, we have to start again. Okay, this is the bearing gain, simulated bearing gain for ACS InnoSat plant. What it is one of the type of the disturbance that can disturb our signal. In a sinusoidal pattern, the value of gain cannot range from a maximum of 1.5 to minimum 0.5, and the bearing gain simulated the InnoSat parameters gradual adjustment over time. And this is the equation. K0 equals to K1 plus O 0.5 K1 sine 0.01 K. Okay, this is the bearing gain lah. We show is the sinusoidal waveform. Okay, for the methodology also, here is the three block diagram. Okay, the first one is the PID lead controller design. PID, which is combined with the lead compensator, and then we combine with plan of the InnoSat. Okay, this is the first one. And then this is the second one. Figure 3 shows the second block diagram of MPC lead controller for the InnoSat plan. What we use here, we modify the controller by adding the lead controller in series with the MPC. This is MPC in series with the MPC to produce a better control signal, and also to help MPC to improve the system stability. Okay, the last one is our third design, MPC PD lead controller design. And for this one, okay, we have made from the MPC, we combine in series or in cascade with the PD and also the lead controller to the plant also. And then why we use this? Because we want to give the advantage of the lead controller and PD component. And for the good controller, we should have short rise time, the minimum overshoot, and possible to return to normal operation in the presence of any predicted perturbation. And then one of our perturbation is varying gain. Okay. And then this is the results and discussion for role exists only. Yeah. For role exists only, for the initial condition, we can see that not very stable for our waveform. But after we can see that they can control already. Yeah. And then we can this upper waveform is shown that the fastest controller here that reach the settling time is the MPC lead controller with 25.92%. Okay, and for the moderate controller is MPC PD lead, but very low.
Sorry to interrupt, Dr. Fazila, you have 2 more minutes.
2 more minutes. Okay.
Thank you.
Then this is for roll. And then we have also for pitch exist. Okay. It's happened like that also. And then we have the third one for your exist. Okay, like that also. MPC and MPC PD lead is the best controller. And then when we compare the result for from t equals to 0 second and to t equals to 1000 second, we can see that MPC lead and MPC PD lead is two of the novelty controller. But if we compare after the initial condition, that's mean 200 second to 1000 second, we can see that PID lead is the best controller. Okay, for the conclusion here, okay, we can stated that, yeah, for the conclusion, we can conclude that based on the satellite dynamic model of the 3 controllers used here, this is the PID lead, MPC lead, and MPC PD lead that have been suggested for the satellite attitude control system, and 2 innovative adaptive controller technique for satellite attitude control, MPC lead and MPC PD lead controller. And this study suggests that adaptive controller for nano-satellite attitude control could be used to control nano-satellite system despite operating condition and varying gain effectively. Okay. For further, it's recommended for further analysis. Another possible improvement for the simulation is the incorporation of the InnoSat design system into a graphical user interface GUI that allows a list of instructions to be issued in the simulation at any time, and user can also see simulation output progress data and change the value of the simulation parameter with GUI. Okay, this is 13 of the reference I have been used here. And okay, thank you. That's all.
Okay, thank you, Dr. Fazila, for the presentation. So I now open the session for Q&A, maybe from the audience and also the judges. Okay, we have one question from Professor Madia, Dr. Muhammad Azwadi. It's any type of antenna is used in this project?
In this project, we don't use any antenna for this project because we just control the satellite to rotate the orbit, and we have to improve the circulation with the good with the best to reduce the disturbance, like bearing gain. That's what we have. 4 of the disturbance, but I'm not give all of my disturbance in this paper.
Okay, so this simulation is based on results or any experiment?
Yes, this is based on simulation of the result. We have the coding. We run the coding and we make sure that if there any disturbance like bearing gain or any other disturbance, then we can see from the slide. Okay, we can see from the slide. Okay, we can see from the slide. At the initial condition, it cannot what to say? It cannot show the any very big disturbance here, very big disturbance. But from time to time, the controller can adjust their signal into the best signal, into the best situation. In this one, we can see that, okay, from 200, okay, after the 200 to 900, we can see that PID controller is the best. Why PID controller is the best? This is because integration, yeah, integrated in the controller. PID, P mean proportional, integral, and differential. The integral one used to make the minimal of the error here. Okay. That's all.
So thank you, Doctor, for the presentation and also joining us in Iconbet 2025. Okay, so next I would like to invite our second oral presenter and also the last presenter for morning session. So please join me in welcoming Dr. Ahmad Zul Izi Fauzi. Will be presenting his work on computational fluid dynamic based investigation of temperature distribution in office air conditioning system. So Dr. Zul Izi, you can proceed with the presentation. You have 10 minutes for presentation and 5 minutes for the Q&A. Okay.
Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. Thank you, Mr. Chairperson, for inviting me for this presentation. My name is Ahmad Zul Fauzi from Faculty of Bioengineering and Technology, UC Malaysia, Kelantan. Okay, it's an honor to present our recent study titled Computational Fluid Dynamic Based Investigation of Temperature Distribution in Office Air Conditioning System. This collaborative work is a part of our initiative to support energy efficient and thermally comfortable office environment through simulation and experimental validations. Let's begin with a brief background of the problem. Okay, in many office buildings, maintaining thermal comfort while reducing energy consumptions remains a challenge. Uneven temperature distribution is a common issue. It's not only reduce occupant comfort, but also increase energy use due to habit overcompensations. To address this, we use CFD, computational fluid dynamics, a powerful tool for analyzing airflow and heat distribution with high resolutions. However, most previous studies lack real-world validation, which limit their practical applications. So our research is aimed to bridge this gap. Okay, the study had three main objectives. First, to model a standard office room using CFD in SS Fluent. Second, to simulate temperature distribution based on realistic boundary conditions. And third, to validate those simulations with actual measurement from a physical office environment. Okay, with the objective in place, I walk you through the setup of the office model we used for both simulation experiments. The room office had realistic proportions. Sorry. Okay, the office room had realistic proportion. The size is 3.8 by 2.5 by 3.7 meters with a standard work table. With the standard work table, glass window, and a wall-mounted split air conditioner type unit. This configuration is a real measurement of an office on our campus and provides a reliable foundation for validation. For the methodology, we use ANSYS Fluent for the simulations. The model employed an unstructured tetrahedral mesh with over 29,000 nodes and 150K elements. This allows us to capture airflow behavior near walls and the AC outlet. Okay, the simulations apply a pressure-based solver with buoyancy, enable the energy equation, and was run for 200 seconds with a 0.5 second time step. So 400 in total. Okay, for validation, to validate the simulation, we use HTC1 digital thermometers that placed at 5 strategic points in the room, the centers, corners, near the door and window. This point was chosen to capture spatial variation in temperature. The room was allowed to stabilize before data logging, and readings were taken every 20 seconds for a duration of 200 seconds. And this matching the simulation timeline. Now I share how the simulation performed against these measured values. From the result of the validation, we found out that the CFD model will perform very well. The RMSC values were below 0.3 degrees C in 4 of our 5 locations. And the mean absolute errors were all within the acceptable bounds. There is a slight deviation in area 1, suggests convective or thermal boundary simplifications. The highest deviations occurred at the room center. That is possibly due to the air mixing effects that's not fully captured by the model. So overall, the simulation showed strong predictive accuracy. Okay. Now let's take a deeper look at how the cooling trends evolve over time. Here we compare the temperature change over time at 5 monitored locations. The trend between measured and simulated data are remarkably consistent. The area 5 that was closest to the AC vent showed the fastest cooling, while the area 1 and 3 had slower responses, indicating reduced airflow or limited circulation. This pattern validates the CFD's ability to model dynamic cooling behavior. And it's important to highlight that the rate of temperature drop reflects not just the airflow velocity, but also the local turbulence intensity and how the air is mixed within a space. In practical terms, this means that even small obstructions or poor vent positioning can create uneven cooling zones. And from a design perspective, identifying these patterns allows engineers to better place air outlets or redistribute furniture to promote more uniform in air mixings. Additionally, this result reinforced the need for transitions in the CFD analysis in enclosed space, as statistic simulations might miss this early stage cooling dynamics. Overall, this agreement between the simulated and measured trends support the reliability of the model for predicting real-time cooling response in office environment. Okay, this is result for spatial distribution. It shows the visual map of the temperature distribution before and after 200 seconds of cooling. Before the cooling, as you can see from the left image, it can be seen that the room was uniformly warm with an initial temperature approximately 26.2 degrees Celsius across all areas. And for the after 200 second simulation, as you can see from the right side, there's a cool zone developed near the air conditioning vent where cool air was injected into the room. At the same time, warm pockets persist near the window and the corners, particularly in the area 3 and 4. Okay, this non-uniformity indicates that room layouts, including the position of the furniture, the geometry of boundaries, and the most importantly, the vent positioning, shows that it significantly affects the thermal performance. The simulation clearly shows that even within a relatively small enclosed space, the airflow does not distribute evenly unless the layout is optimized. The air near the vents travels and cools the space efficiently, while the stagnant zone or near the corner or near the thermal barriers are left inadequately ventilated. Okay, from a design standpoint, this insight can help the facility engineers or HVAC planner to refine the vent placement and access where additional calculations.
Dr. Zul, you
Yes,
have 2 more minutes. Sorry to interrupt.
Okay, sorry. All right. I'll pass it up. Okay. Additionally, this result support an idea that simply increasing cooling capacity isn't always effective. Instead, improving air distribution based on validated spatial analysis can lead to better thermal comfort and with lower energy consumptions. And this highlight the value of spatial CFD visualization as a diagnostic tool and that's diagnostic and planning tool in both new building and retrofit scenarios. Okay, to summarize, we had developed an accurate CFD model that captured both temporal and spatial cooling behavior. That model will align well with experimental data and it's reinforcing its reliability. We also identified the problem zone that commonly go unnoticed in HVAC design, and this can inform better layout and ventilation strategies. For the future, we plan to expand that model to multi-zone spaces and also integrate real-time control elements. Okay, before I end, I'd like to acknowledge our sponsors and partners. This study was funded by Ministry of Higher Education Malaysia through FRGS grant. We also thank the Next Research Group at BKT, UMK, and our collaborators from Energy Commission and Universiti Kemasyakan Malaysia. Their support was instrumental throughout this project. And our reference include key publication in CFD validation, thermal comfort, and indoor environmental simulation. All the other details of references are included in the full paper. With that, I now welcome any questions. Thank you.
Okay, thank you, Dr. Zul, for the presentation. I now open the session. Okay, so very quick. We have one question from Dr. Hidayani. Okay, how accurate are CFD models in predicting real world temperature gradient in office?
How accurate?
Yeah, how
okay,
accurate?
for the accuracy, I make a validation study and I compare with the experimental result and simulation result. And I use RMSE value to compare. From the analysis, the RMSE value and mean absolute error were limited, were minor. So for me, I think the simulation is quite accurate actually. And we also using the SRS standard, M55, to make a reference for positioning of the sensors to make a validations. We follow the standard.
Okay, so I hope the explanation answered the questions. And we have another question from Dr. Iqbal, I guess. Dr. Zul, how do you define the turbulent model in this case?
Sorry, turbulent model.
Or maybe Dr. Iqbal can expand a question a little bit.
Okay, I can see the question from the chat box. Of how you define the turbulent model in this case. Okay, in the study, the turbulent model is applied to simulate the airflow and temperature distribution with within a confined indoor environment. Okay. Due to the nature of ventilation system and the complexity of recirculating airflow, the turbulent model is essential to accurately predict the flow. So for the turbulent model, we use a standard KE model, K epsilon model, that used for general purpose indoor airflow. And we also compare the ING K epsilon model. But for this paper, I not yet published the result of the comparing the different model for this paper for Iconbet. But in the future, this result for the comparison of the model will be included.
Okay, thank you. So I hope the explanation answered the questions. Okay, so with the end of the presentation from Dr. Zul, we come to the end of our session. Our morning session today. So before we adjourn, let's have a photo session. So I would like to kindly request all of the audience to open your camera. Okay, let me do the setup. Okay. Okay, so get ready. 1, 2, 3. Okay, one more. Okay, ready? 1, 2, 3. Okay, so thank you everybody for the great session this morning and this afternoon. So with this, we adjourn the session, the morning session, and we will resume for the next session scheduled in 2:30. So once again, I thank all of you for your commitment today, and see you again in the next sessions. So bye-bye, everyone.
Okay, thank
Bye,
you.
thank you. Assalamualaikum.
Waalaikumsalam.